Hello, we're Team 25506. Our project is the Mobile Telescope Transport System, or MTS. Our goal is to design a self-contained transport, power, and operation system for a 1-meter Cassegrain observatory class telescope. This allows observatories to deploy in remote or under-resourced locations without needing permanent infrastructure. Over the next few minutes, we'll work you through how our cross-disciplinary team brought this concept to life.
All right, I'll be going over the problem statement. So, fixed observations face challenges like limited sky coverage, environmental exposure, and high infrastructure costs. Our sponsor needed a mobile alternative that could safely transport and operate a precision telescope in harsh environments. This includes handling vibration, power needs, and optical alignment, all while being easily deployed in the field.
Our system is built on a gooseneck trailer platform reinforced to support over 5 tons. At its heart is a rotating dome with a sliding shutter that protects the telescope and enables full sky access. Power is provided by a solar-charged modular battery system, eliminating the noise and the vibration of a generator. HVAC maintains stable interior conditions, while onboard communications allow for remote control.
A major focus of our system design was the rotating dome enclosure that houses the telescope. In the original design, we used a basic roll-off or slide-away structure, but after calculations and analysis, we upgraded to a fully enclosed rotating dome. This update dramatically improved durability, weather protection, and observational flexibility. The dome expanded viewing aperture was one of the first enhancements. By increasing the window size, we gave the telescope a much broader field of regard, improving the range of celestial targets it can observe without physically moving the trailer. This also improves mission versatility, whether it's for deep space tracking or low elevation atmospheric measurements. We then integrated a retractable garage-style access door. This design simplifies setup and teardown by allowing operators to slide the opening instead of lifting or rotating large panels. It also improves the seal against dust, moisture, and wind, which is critical during telescope deployment or transport. Finally, one of the most practical features is the dome's modular construction. Each dome segment can be removed independently, which allows the entire enclosure to be packed down for transport. This is especially useful when height limits are concerned, for example, driving under an overpass or storing the unit in standard industrial buildings. With the dome disassembled, the total trailer height drops below 14 feet. On site, the pieces can be reassembled quickly without needing cranes or specialized hardware. Together, these upgrades make the dome not just a protective shell, but an integral part of the mobile telescope system's flexibility, reliability, and long-term usability.
As discussed before, with our modal analysis covering the full MTS frame in accordance with MIL Standard 810H, using method 514.8, which is our standard for vibration evaluation of sensitive equipment during ground transport. Our analysis identified the first 5 natural frequencies at 1.6, 2.7, 4.35, 9.19, and 11.69 Hz. These are well below the high frequency region where optical performance would be affected. We then evaluated the performance of our elastomeric vibration isolators. Using transmissibility calculations, we confirmed that the isolation system provides greater than 90% attenuation for vibration energy above 100 Hz, which exceeds the requirement of at least 80% reduction. Because the natural frequencies are outside critical excitation bands and the isolators significantly reduce transmitted vibration, the requirement is verified by analysis. No physical testing was done, as this is a conceptual project.
We ran full structural and vibrational simulations. After relocating the telescope to the trailer center, our stress test showed a factor of safety of 4.6. Modal analysis confirmed reduced vibration amplitudes due to mass centering. Our electrical design includes a 30.6 kilowatt hours of battery capacity, delivering 10 kilowatt hours at 240 volts. Solar panels provide about a 13 kilowatt per hour day, which supports multiple days of operation, even with overcast conditions.
So we redesigned the dome for rotational mobility and integration, thermal shedding. The telescope mount provides clearance, stability, and protection during transport.
We use dual AC500 inverters along with 10 BC300S batteries, smart controllers, and with redundancy built in. Performance tests can perform over 6 hours continuous load operation.
HVAC is sized for desert and cold climates. We maintain 68 to 77 degrees Fahrenheit inside with smart humidity control.
We also developed a full verification matrix and FAT plan covering power, structure, and communication.
Once deployed at a remote site, the mobile telescope system is leveled using its stabilizing jacks. The solar array, 3 panels on each side, recharge our battery bank throughout the day. That stored energy feeds our battery and inverter system, which powers the telescope, dome rotation, communications, and environmental controls with no generator required. During observing, data from the telescope is recorded on our onboard server rack. Once captured, the system uses Starlink to upload the results to the host site for remote access and processing.
The sustainable modular design of the MTS allows for reuse due to its ability to be relocated and end-of-life recycling of core components. It reduces material waste and minimizes site and habitat disturbance. Since it is relocatable, the MTS is ideal for temporary deployments in remote locations and avoids permanent placement on culturally sensitive or sacred lands. Its reliance on solar power for energy needs reduces the MTS's dependence on fuel and maintenance-heavy generators. The MTS lowers the barrier to entry for institutions and communities, fostering broader public participation and engagement in astronomy, especially for underserved groups. It opens doors for schools, amateur astronomers, and researchers in developing regions to access cutting-edge tools. The MTS enables field research, STEM outreach, and global collaboration without fixed infrastructure, heavy dependence on fuel, and avoids impacting cultural or sensitive land and resources.
Team 25506 thanks you all for your time and support. This project challenged us to combine engineering rigor with real-world constraints. We're proud of the outcome and very excited to see where it goes next. Thank you.